Welcome to Homework Lib.
Okay, in problem 102, we have a concave mirror and a firefly, which is 4 millimeters tall. And we're also given a plot, which is a data set of 5 points. And your plot is given on the horizontal axis 1 over the magnification, and the vertical axis is S, which is the object position. And I've only reproduced 1 point here, which is 1 over m at minus 1, which corresponds to a S of 50 centimeters. And this is supposed to be a straight line. And in part A, we're asked why this data is a straight line. So to see why that is the case, let's use 1 over S plus 1 over S prime is equal to 1 over F. Now for your mirror, obviously F, the focal length, is fixed, right? It's fixed by the radius of curvature divided by 2. So this is a constant number. So only S and S prime are changing. So if you change the position of your object, position of your image changes, but the focal length here remains the same because we're not changing the size of the mirror. So what we will do now is use this equation and also the equation for magnification, which tells us that it's minus S prime over S, and that's the image distance measured relative to the vertex of the mirror, and it's the object distance measured relative to the vertex of the mirror. And what I want to do is, since our data is given in terms of 1 over m, let me just rearrange this equation to get 1 over m. So then 1 over m is minus s over s primed. Okay, and what I'll do now is solve this first equation for s prime and then substitute it in here so that I have an equation that's just that just depends on s, m, and my constant f, right? So then I have the s prime. So then I can have something that gives me s as a function of m, or 1 over m rather. So if I solve this equation for s prime, so I have 1 over s prime is equal to 1 over s minus 1 over f. And that tells me that 1 over s prime is, I have this backwards, so that should be minus 1 over s plus 1 over f, right? So 1 over s prime is now s minus f over s times f. And then that tells me that s primed is s f over s minus f. And now if I substitute into my 1 over m equation, so I'm going to substitute this value in here. So then I will get 1 over m is minus s divided by s prime, which is now s times f divided by s minus f. And that gives me s, so I can bring this to the numerator divided by sf, and I can cancel out this common factor of s, so then I have 1 over m is equal to s minus f divided by f. And if I wanted, I can solve for s as a function of m, meaning I can isolate s and write it in terms of m. So I can rearrange this thing, and that will give me that s is f times 1 minus 1 over m. Okay, so we'll use this equation, and at some point we'll also make use of this equation. Anyhow, you see here that s is linear in 1 over m. So if I have 1 over m on my horizontal axis, then my s will give me a line according to f, which is just a number, times 1 minus this variable 1 over m here. So that's why we have a line. And now we have to use this plot to determine the focal length. So I have picked out this one point here because it seemed the clearest point to me on the plot, because this horizontal axis was easy to read, and it seemed fairly easy to deduce that this corresponds to 50 centimeters. But you can use any other point if it's obvious to you what those points are. So I'm going to use this equation that I just found, that s is equal to f 1 minus 1 over m, to find f. Because for my plot I have 1 over m and I have s, so I can find that f is equal to s divided by 1 minus 1 over m. And I have a s of 50 centimeters divided by 1 minus 1 over minus 1, which is 50 divided by 2. And that's 25 centimeters. So that's our focal length for this problem. So this problem is pretty long. It has several parts. So let's continue. In part C, we're asked how far from the vertex should the object be, which I denoted by s, for an image height y prime to be inverted. So I have that negative number to be inverted and has a magnitude of 8 millimeters. So now we need to determine s for an image height, an inverted image of 8 millimeters. So we were given that the object height y is 4 millimeters, right? And what we'll do in this case, we're going to write that m is y primed over y, and we know the image is inverted, so we have minus 8 millimeters divided by 4 millimeters, and this corresponds to a magnification of minus 2. And I want to find s, so I can use this formula right here, which we derived. And let's write down the formula. S is f times 1 minus 1 over m. We found f in part B, so that tells me that. And we just found m earlier in this portion, so we have 25 centimeters. And then that's 1 minus 1 over minus 2. So this really is just a factor of 3 halves. So that's 25 times 3 halves, which gives me 37.5 centimeters. So this is where I need to put my object if I want a 4 millimeter object to have an image height of 8 millimeters. In part D, they ask if you want to increase the image height, should you move the object closer or farther away from the vertex of the mirror? And so in this case, if you look at the plot, that would indicate that you want to move it closer, because this is the reciprocal of the magnification. So as the magnification gets bigger and bigger here, so on this side will correspond to bigger magnification, and on this side will correspond to lower magnification. So we see that it has this kind of downward sloping relationship. So if we want bigger magnification, we'd S to be smaller, right? Because we have this line with this sort of negative slope. So examining that data, we know that we should move the object closer to the vertex. And we'll show this because in the second part of the problem, they ask you where you need to move the object in order to increase the height from 8 millimeters to now 12 millimeters. So again, we'll use this formula and carry out the same steps. So my magnification will be minus 12 millimeters over 4 millimeters, which is a magnification of minus 6. And then identical steps is up here. So S is 25 centimeters times 1 minus 1 over minus 6. And that's 25 times 7/6. And that will give us 29.17 centimeters. So obviously we moved it from 37.5 to 29.17. So we're moving it closer to the vertex of the mirror. And now let's move on to part E. Why does 1 over m go to 0 as your object approaches 25 centimeters, as the object approaches the focal length? And so it turns out as your object approaches the focal length, then your rays of light will form an image at infinity, and when that happens, your S prime is going to be out at infinity, and remember that m is defined as minus S prime over S, so 1 over m is minus S over S prime, and if S prime is going to infinity, that gives me something that goes like S over infinity, which should go to 0, because S is finite and this is infinitely large. So that's why 1 over m goes to 0 as S goes to F. And will the image be sharp? No, because you're not focusing the rays on it. on a particular point, your S prime is now out at infinity. And now in part F, why can't you have sharp images formed for the object distance that's inside the focal length? So now less than the focal length, which here is 25 centimeters. Well, it turns out you're going to have a virtual image because your rays are going to diverge instead of now converging to when you're inside the focal length, your rays are going to diverge, and then you're going to have a virtual image, that's like behind the mirror, instead of the case of when you're now outside. Let's say your focal point is here, and your object is here. Then you will have some image down here that's real, like so.